Hi guys, good evening. Happy Tuesday to all. Um, as Mel said, I work as a team lead for the tech support team at Skill-Lync. Uh, we have a lot of courses that pertain to various applications of CFD, and we try to tackle a lot of these things uh, in our day-to-day life, where students come to us with their doubts, their resolutions, their projects also. At the same time, the courses that we have on our website right now, they pertain to a lot of industry relevant tools, uh, software packages, and we try to teach from base level to advanced level. In today's topic, I wanted to tackle something interesting. This is a direct application of what CFD is trying to do, really. So CFD stands for computational fluid dynamics, where essentially in computational fluid dynamics, we want to understand how fluids are behaving uh, for a certain application, for a certain given use case. How your fluid will fare is what we are trying to understand by making use of numerical approaches, by making use of computer software. We just try and understand how your fluid will behave in a certain uh, application. So in today's topic, we will understand what batteries really are, why do we want to cool them, how do we manage the uh, heat that is being produced in batteries. So in today, I'll try to explain a bit about the background, why we are actually trying to move more towards battery research and what are their major use case, the electric vehicles, then the individual, what exactly is a battery, what are the individual components present in a battery, then what is thermal runaway, which is the major problem that is tackled due to heat within a battery, then how is battery thermal management done, and towards the end, what are the analysis techniques we use to understand the BTMS. So first things first, why exactly are we interested in batteries? I'm sure you guys have seen such images in your daily life in news where an electric vehicle suddenly catches on fire because the batteries present in these vehicles were not uh, accounted for cooling. Essentially any battery that comes out with an electric vehicle is made out of lithium-ion batteries, and lithium-ion batteries really do not want to get hot. And for a country like India, we really cannot afford to get any of our electric vehicles get heated because we are a tropical country and the average temperatures range about 35 and above. So for such instance, in a closed sort of a box, sort of a formation within an electric vehicle, the temperatures can very well reach above 40 degrees Celsius, which is really not good for the materials that we use to manufacture these batteries. So coming down to even further, why exactly do we need an electric vehicle if these are the demerits? Well, we want electric vehicles because the vehicles we currently have, gasoline, diesel, these vehicles are using up a lot of non-renewable sort of resources such as your petroleum, and day by day we see petroleum prices keep getting high, the prices keep skyrocketing. Along with that, there is the added disadvantage of increase in pollution in our environment. There are studies that show that cities like Delhi, you know cities like Lucknow, these cities have become major hubs for a lot of particulate matter. uh, so this particulate matter, when it goes into your lungs, this is not really good for your health, and the amount of these particulate matters is measured in ppm, that we call parts per million. So the ppm generally needs to be lesser than 50, and till 100 it's a bit acceptable, but on a regular basis, city like Delhi reaches around 300, 400 ppm, which is really really not good. It is equivalent to, studies say that it is equivalent to a person smoking for like 2-3 years, and your lungs would look like that if you stay in Delhi. So in such cases, we really need electric vehicles which are offsetting your energy, or offsetting essentially the pollution from a small car to a full-blown uh, power plant. For example, the electricity that comes to the electric vehicle also comes from a power plant, because India is majorly getting its power needs from non-renewable resources itself, but the difference is the energy efficiency that we get. In that, the amount of coal that would produce a certain amount of pollution would give you more amount of electricity and more amount of equivalent power than a single car would give you with same amount of pollution versus same amount of fuel that is being used. So for that matter of fact, we prefer the offsetting of this energy, whereby we want to use electric vehicles as much as possible so that the energy is a bit offset. Now, electric vehicle consists of various parts, components of its own. There is your electric motor, transmission, motor drive, the battery converter, onboard charger, auxiliary battery. And on the bottom, you can see the battery bank. It's kept on the bottom because the center of gravity for your vehicle should be low. The lower it is, the better it is for the stability of your vehicle. Now, it's important to note that the batteries are kept at the belly of the car. We'll come back to this in just a moment. Now, the different battery types, as I spoke, the majority of batteries that we use right now are lithium-ion. The reason why is evident right here. This is your energy density versus the weight that is carried. In that, we want to pack as much energy as we can within small weight, because this battery pack that we see on the belly of the car needs to be as less weight as possible so that you can carry more payload through the entire car. Lithium-ion is one such battery pack which hits a good checkpoint where it has higher energy density, whereby it is still carrying more amount of weight, but it is lesser in a way, and it is rechargeable. It has more number of charge cycles. Along with that, we have been able to get to a safe sort of a situation where we can safely control what is happening within a lithium-ion battery. Once again, yeah. So the principle of lithium-ion battery, for any battery, it is quite simple. There is an anode, then there's a cathode, and there is a flow of electrons from one part to another based on whether it is charging or discharging. For charging, the electrons flow in to the anode, and electrons basically move from anode to cathode through an electrolyte. So think of it in terms of water flowing from a tank above your house. So the more you have water, the faster the discharge rate you can get in your pipes. The lesser the water, the slower the pipe discharge rate will be. Same principle can be applied to your batteries as well. If the amount of electrons you've packed in, or the ions that have been formed are packed in more, then it will give you a good amount of power. Otherwise, it will not. Along with that, for discharge, the ions move from cathode to anode. In that, the electricity is generated in that fashion, and ions move in that way. And as you can see on the right, this is sort of a general view of what a battery really looks like. There is a casing that is made very meticulously so that the lithium ion or lithium that is packed within this battery is not exposed to air. The reason why is because lithium, when exposed to air, it's highly reactive and it can catch fire very quickly. So the structural integrity of a battery is very, very important. Now, what exactly is in a battery pack? So in battery pack, there are a series of cells which are kept inside each module. Now, cell is a singular unit which converts the chemical energy into electrical energy, and a collection of these is called a module, which can be connected in series or parallel. In that, the cells are connected in series or parallel based on their use case. And a pack consists of a series of such individual modules. Now, the reason why we want to discretize, or we want to distribute the power generation in such a way, is that if we have any error that has occurred, or any sort of a hazard that has occurred, it can be controlled to a smaller area, and we can very quickly cut off the power supply and very quickly make some sort of a checkup there so that it's not spread to other packs as well or other modules as well. Right. This is pretty basic. Again, batteries connected in series or parallel. If you can see, for a battery which is of a maximum voltage 4.2 volts, if they are connected in series, the voltage increases, but the ampere or the amps, the 3400 milliamp hour that you can see right here, this does not increase. So can somebody quickly tell me what is voltage? What exactly do we mean when we say voltage for a battery? Great. Potential difference. What do we mean potential difference? What is potential in this instance? Okay. Okay. So great answers, guys. Coming back to the analogy of a water tank kept on the top of Great Allen. Yes. Yep. Coming to the analogy of a water tank kept on top of your house, the more amount of water it can carry, the better the discharge it can provide. So the difference in concentration of charge is what we call as voltage. Great answer. Now, what do I mean by amps? What do I mean by current? Anybody? Great. Great. So amp essentially is measuring, amount of electrons moving past a point in a second, or essentially it is the flow of charge is what we're trying to measure here. Now the mAh that we see right here, milliamp hour, this essentially means that this one cell can give 3400 milliamps for an hour. Now, when I put these three cells in series, they can provide me with 12.6 volts of maximum voltage, but will only provide me with 3400 milliamps for an hour, or it will flow for one full hour. But when I look at parallel connection, there are 6 batteries that you see right here, all of them at 4.2 volts. When I use parallel, the amount of voltage that I can get, or the potential difference that I can get, is pretty much the same 4.2 volts. But the amount of time that I can take out this 4.2 volts of voltage significantly increases. So I can have 20,400 milliamps flowing for an hour. That's the basic difference between series and parallel. So based on use case, based on what exactly is the use for such a configuration, we decide whether we want to keep our batteries in series or in parallel, right? So yeah, this would be what your batteries would look like in series or in parallel, based on how you want to connect them. So the top view that you see right here, the snake sort of a view can be kept. But for parallel, they are connected, from positive to negative and whatnot. Now, what is C rate? C rate is also something quite interesting. C rate talks about what we just spoke of, the load or the milliamp hour. So C rate essentially that you see right here is a unit to declare current value, which is used for estimating or designating the expected effective time of battery under variable discharge, charge or discharge. So for a battery of 1000 milliamp hour, if we want to take up, 500 milliamps in an hour, then essentially we are taking half the load. But for 1000 milliamp hour, if we are taking a load of 1000 milliamps, this is what we call as 1C. In the previous case, when the battery is kept at 1000 milliamp hour and the load is 500, can somebody tell me what happens to C? For let's say input to output, let's talk about it this way. Input for the battery we currently have is 1000 milliamp hour. The output that we take out is 1000. We are saying that the C rate is 1, but if the input is 1000 and the output is 500, what would be the C rate? Are you sure, Subhatra? So look at what's happening here. If I have 1000 liters in my tank and I'm taking away 500 in an hour, then do I not have one more 500 liters present that I can discharge in one more hour? So what happens to C rate now? It doubles, correct? So the C rate for the first case would be 2C. For the second case, it's C. For the third case, when I have 1000 milliamp hour, but I'm taking a load of 2000 milliamp hour, it means that my battery can only operate for 30 minutes or half the hour. In that case, my C rate will become 0.5 C. Right? Great. Think of it in terms of a water tank versus the amount of discharge that is being taken out. If the amount of discharge is higher, then the battery cannot sustain for more amount of time, and we have decimal point in what the C rate will be. Whereas if the load taken out is lesser than what the battery actually carries, then your C rate will be higher. C rate essentially is the estimation of what is the effective time for which battery can work. That's the whole point. Okay. Now let's talk about thermal runaway. So far we spoke about what is a battery, what are the different components of it, how do we set them up, series, parallel. Then if there is series, then what is the point there? If there is parallel, then what is the point there? At the same time, we spoke about C rate as well. Now let's talk about thermal runaway. Now, major reason, first I want to explain to you guys what exactly is happening that causes batteries to get heated up. So I'm sure you guys are aware of this formula. It's called I square R, which gives you the power generated within an electrical circuit. The idea is that when electricity is flowing in any conductor, the electricity is going to generate certain form of energy. Now this energy can be translated into heat energy as well. Can somebody tell me why any conductor that gets heated up or that gets electricity flown through it gets heated up? Think of it as your general water heater that you have at home that you plug in and then put inside a bucket, correct? And the water inside your bucket sort of gets heated up. Can somebody tell me what's happening there? Yes, resistance. Okay. So what is resistance and why is it making my conductor get heated up? Great. Come on, guys. Okay. Okay. So resistance essentially talks about, great answer, Alan. Okay. So resistance essentially talks about the resistance of flow of electrons, in that the material doesn't really want electrons to flow through it because the molecules, atoms that are present inside that component, they are very closely packed and they do not want charge to flow through it. When that happens, there is a collision between molecules, and for solids, the molecules are so closely packed that they tend to vibrate. When they tend to vibrate, they generate a sort of kinetic energy, and this kinetic energy is translated to temperature. Now, what does this mean for batteries? For batteries, this means that whenever electricity is sent to them or withdrawn from them, there is a chance that these molecules will tend to vibrate, and this vibration will translate to heat. Now, when electricity is sent to the batteries, there is a cap or there is a limit to how much electricity we can send to the batteries at any given point of time. But when we take out electricity, there is no real limit of how quickly we can take out, as we saw in the C rate. So even if it was a 500 milliamp hour battery, we can take a load of 2000 milliamp hour, which makes the C rate to be 0.25, 0.25 C. In that, the battery will work only for 1/4 the time it was supposed to work, or it will only give me 2000 milliamp hour of current for 0.25 hours. So when I'm discharging the batteries in such a huge load, this means that there is more amount of flow of electrons through that battery, which makes the heat energy much more significant. So for such cases, it's evident that batteries obviously generate heat, and when they generate heat, it is really bad for the battery pack itself. Now, what happens at different temperatures? Essentially, let's talk about at 80 degrees Celsius, let's say. Now, the solid electrolyte interface, it starts to decompose. What does that mean? It means that now there is a free flow of electrons between the anode and cathode. Now, at this temperature, the electrolyte really breaks down. This means that now lithium-ion has a free rein on how it wants to move within or outside the battery. At 120 degrees, 130 degrees Celsius, the separator now melts down. This causes an internal short circuit. At 130 to 150, now the positively charged cathode, it begins to decompose, and now it is going to produce oxygen. This is really bad because if lithium is going to react with oxygen, now that generates a lot of heat. Or lithium is the chemical reaction of lithium with oxygen is very exothermic, and it's very rapid as well. At 150 to 180, the cell becomes very unstable, and in this case, thermal runaway happens. Now, thermal runaway is essentially the condition in which battery, the full battery, will catch on fire, and this can be, translated from one damaged cell to another damaged cell. Now, thermal runaway can take place in less than 10 seconds. The amount of heat generated is of the order of 10 to the power 7 watts per meter cube. So the desired operating condition or operating temperature range for a battery is kept at 15 to 35 degrees Celsius only, because beyond that, the battery can obviously sustain, but it has its own implications on the material that is holding the battery pack together. So over a repeated, let's say over a year, if the battery is kept at 45 and above degrees Celsius, the materials that we have used to manufacture the batteries will undergo sort of a fatigue due to repeated thermal loads, thermal stress. And this may cause the battery pack to develop cracks, develop structural sort of deformations. And because of that, your lifetime of a battery may reduce significantly. So the operating temperature is kept to a minimal between 15 to 35. So as you can see, this was outside Delhi Metro. There was an electric scooter that was kept near a charging point. And because this was summer and there was no real active cooling that was happening for the battery pack as well, the battery pack got on fire. Fortunately, there was nobody that was injured, but you can assume that if this had transported to this full battery pack, or all the individual cells inside this battery pack, if they had caught on fire, then a catastrophe would have happened. All right, now let's talk about the battery thermal management system. We've learned why do we exactly need batteries to be as cool as possible. Now let's talk about how do we do it. Now, there are different ways. There are active methods that you can use in cooling down your batteries as quickly as possible. Now, major points or major factors to notice here is that within a battery pack, the temperature should be as uniform as possible, or the temperature distribution within the pack should be as uniform as possible. There should be no scope for hotspots. Or if you can see right here, the temperature is nearing 28 to 30 degrees Celsius. This should not happen. Why is that? This is because if there are hotspots within the battery pack, this can lead to a localized sort of an increase in temperature. And this again can lead to a reduction in the life cycle and cell performance itself. So it is recommended that the battery should be kept in such an orderly fashion that air or any cooling methodology that is used can be distributed uniformly. So for this reason, battery thermal management system is really, really important. And it needs to, work properly every single time, or for every single discharge, every single load that comes your way, so that your batteries can work at their peak efficiency and can enhance the overall performance of the vehicle that you're trying to drive. So what exactly consists of BTMS? There are different ways in which you can cool down your battery packs. There is your liquid cooling, there is your air cooling, versus there is your phase change material, or what we call PCM. Within liquid, you can fully immerse the batteries in a liquid. Can single cell failure fail the complete battery pack? Yes, it can happen. So again, as I spoke about the localized sort of hotspots, this may lead to, localized sort of hotspots, this may lead to very high increment of temperature within this zone. If that happens, then there is a possibility that this sector can then increase its heat. If heat is increased in this sector, this very quickly flows down the chain and can damage other batteries also. Okay. So for liquid, there are, you can either fully immerse your battery pack in the liquid and then have the liquid flow through the batteries, or there is an indirect sort of a cold plate or a jacket of liquid that can flow around or over your batteries. Then there is your air cooling, one of the most used. There is your natural versus forced convection. For natural convection, I will show you the test case using OpenFOAM. For forced convection, you can think of your laptop fans, in that how your laptop fan is kept above the processor and how it is extracting heat away from it so that your laptop doesn't get heated up. Now, there are different optimizing techniques that can be kept for air cooling also, in that you have to avoid such localized hotspots and at the same time keep the average temperature of the battery pack to as minimal as possible. Then there are different ways in which you can figure out how your battery should be or the cells should be laid out, how the air channel needs to be designed in the best way possible, and where should you really keep the cooling fan. And towards the end, we have PCM, the phase change materials. In that, think of, your wax, let's say. If wax is heated up, then it very quickly melts. Essentially, the point is that it is absorbing the amount of heat that we are providing to it, and it is converting it into a phase change. So such methods can also be employed for cooling down batteries, in that when batteries are heated up, they will absorb, the phase change material will absorb the heat, then they will undergo a phase change, and then they will come back to their original phase when the temperature has been reduced to normal. Okay. The major sort of way in which we try to cool down the battery pack is through convection. Now, can somebody tell me what is convection? Very quickly. Great. Great. Altaf. Okay. So it's not really limited to liquids. It's more like a, so think of it this way. If you happen to go around and see a river and you throw a certain leaf in that river, that leaf gets transported along with the water in the fashion or in the way in which the river is moving or the water in the river is moving. So the leaf is getting convected in both time and space. Convection essentially talks about the transport of any property in time and space within fluids. In that, if there is heat that is, for instance, if you can see in this graphics card example problem, if heat is getting generated in this graphics card and you have a cooling fan that blows air in this orientation, then this heat is getting transferred from the graphics card to air, and from air, it is getting transported in space and time away from this graphics card. That's your regular convection, where we want heat to be transported from one point to another because we don't really want heat to be kept in one location. All right. This essentially comes from the Newton's law of cooling. Newton, the great guy, has made so many things and also made our lives a bit difficult. But along with that, he also gave us the Newton's law of cooling. In that, he speaks about the convective heat transfer, heat between one point to another. is a function of the normal surface area and temperature difference, then there is the proportionality constant. It's called the heat transfer coefficient. We'll come to this heat transfer coefficient in just a moment, but the idea is that heat transfer is very dependent on difference in temperature versus the surface area through which heat transfer is happening. And also, there is the Reynolds number concept, which also comes into play because we have flow of fluid. Reynolds number is a measure of, the interaction between the fluid wanting to flow versus the inherent friction within fluid that doesn't want the fluid to flow. So it is a ratio of inertial forces, or the force that wants the fluid to flow, versus viscous forces, the force that wants the fluid to come at rest. Now, the segregation, or the sort of general rule of thumb, is that for internal flows, anywhere less than 2300 will be your laminar flow, versus anything greater than 4000 is your turbulent flow. And for external flows, anything less than 10 power 5 is laminar, anything greater than 5 power 5, 10 power 5 is your turbulent flow. And within these ranges, we call this translation or transitional zone, in that your flow is semi-laminar, semi-turbulent. Reason why we do this is because we want to really understand if the flow becomes turbulent, because it has its own implications of how the fluid is going to carry this heat along with it. So that's where your Reynolds number concept comes in, and this is the formula to calculate for that. And then there is the Nusselt number. Now, Nusselt number is the ratio of convective heat transfer to conductive heat transfer. This gives a good idea of which heat transfer is dominating. In that, is my fluid effective enough to carry the heat away from the battery pack, or is the heat from battery getting increased so much that the fluid is not able to carry it? So the higher the Nusselt number, the better the heat transfer, or better the fluid is able to take heat away from the solid. Lesser the Nusselt number, lesser is the fluid effective in taking away the heat. The different types of convection, there is your forced versus natural, in that if the air is pumped to the hotter body, then heat is taken away. Whereas due to density differences and due to temperature differences, the air around the body can become less dense, and it can flow away. This is your natural convection. So when we talk about air cooling, these are the different types of convection, as if you can see on the left. So what is the heat transfer coefficient, or amount of heat that can be taken away through a surface area, is the measure that we want. So the heat transfer coefficient value that we get right here for gases is between 2 and 25. For liquids is between 10 and 1000. So this is free convection or natural convection. So if you understand from this, you can see that liquids are better able to take heat away from a heated up body, or for that matter of fact, if you have a very hot sort of a for a blacksmith, if you guys have seen, these are the guys who heat up metal and they beat it into shapes which they want. So when the metal really becomes red hot, then they very quickly put that inside a bucket of water, and you can see the solid becoming cold very, very quickly, because water essentially has a higher value of heat transfer coefficient when compared to just air. If the metal bar just exists in air, it will take it a longer time for it to cool it down when compared to water. So forced convection for liquids again is higher, and the forced convection for gases is comparatively lower. So this becomes a trade-off in what methodology we want to use, because not all component or systems really need liquid cooling, because liquids carry with them the added disadvantage of leakages and component damage. So yeah, air cooling has some advantages in that it is low cost, lightweight, longer lifespan. This was employed in Honda Insight and Toyota Prius. This can be either passive or active. Inactive cooling system, the heat removal rate is more than passive, but it again depends on the inlet velocities. Again, for natural convection, that you can see for a simple battery pack, the 8C discharge rate, in that it is discharging 8 times the amount of charge that this battery can actually carry. The heat generation rate is at, heat generation is at 37.65 watts. That you can see right here, the heat has peaked at 400 seconds and it has very quickly reduced. It is evident that there is a hot zone in the middle of this cell, and for natural convection, the temperature is very unevenly distributed along the entire battery. This has its implications on how the battery's structural integrity will be, because this is the area that is subjected to heavy thermal loads. And if that is the case, then this area can experience, bulges or cracks over repeated usage. Along with that, when we do forced convection or air cooling, we've just attached a simple copper tube. Now, the average temperature at this particular copper tube is reached between 47 to 43. In that, there is a liquid that is filled within there's air that is filled within this tube. So the front side of this battery pack is kept with this cooling system, whereas the back side is kept open to air. In that, we can see the difference in how the temperature is. In that, the front side, the heat is getting transported through this copper tube, whereas for back side, it is not getting transported and it is kept open to air. So for such cases, when we are using the heat pipe, the average temperature of the cell remains at 49.39, whereas for cases where we are not using the heat pipe, the temperature reaches around 56, which is really not good. Now let's come to air cooling. So for air cooling, the cooling strategy is essentially kept in that we want the air to flow through or flow between the batteries themselves, so that heat is getting transported from one battery to another and to the outlet. So if you see on top, there are inlet air vents which carry the heat with them, and then they are flown through each individual battery pack and they are sent out in this fashion. So if the for this particular configuration, you can go through this reference as well. For this particular configuration, if the inlet pressure is kept at 100 pascals, the diameter of each orifice is kept at 1.5 mm. The number of rows of orifice is 5, and the discharge rate for these batteries or the full battery pack is at 3C. The maximum temperature with and without cooling reduces from 325.9 to 305.7. Now 305.7, if you convert it to degrees Celsius, 305.7 minus 273, this becomes around somewhere over 32 degrees Celsius, which is manageable still. So in this instance, if we are to increase the inlet pressure, or if we are to use a different gas which has more or higher heat transfer coefficient, we can very well reach a lower temperature. So the point being, due to different configurations of how your air is going to flow through, you can experience different cooling as well. So for instance, in this case, there is a fan that is kept at the inlet. Now in this case, using forced air cooling, initial temperature is at 26 degrees Celsius. The maximum module temperature which can come using forced air cooling can be 42.4. Now we can do both sort of a hybrid thermal management system, in that we can use forced convection when temperature reaches a set threshold, thereby when there is a difficulty in the natural convection not being able to carry heat away from the battery pack, we can very well employ your forced convection and then reduce the heat very effectively. But when it is not required, we can shut this off and have the heat flow through the battery pack in a natural manner. This helps with power consumption for the fan as well. Now again, for air cooling that we can see right here, if the heat is generated in the middle for a case, now if air is sent through when there is no spacing kept between the batteries, you can see heat is localized within these cells. But at the same time, if spacing is given at 2 mm, then again, the temperature is localized within these cells. But If the spacing is kept at 4 mm, temperature is a bit more uniformly distributed, but it is reaching, 43.9 degrees at maximum. Now, which configuration is best depends on a case-to-case basis, because you really can't employ one methodology for all the requirements, but it is beneficial for you to study different sets of configurations of how to keep the batteries, what should be the spacing, that can be employed between the batteries, so that it best, gives you the results, or best gives you the understanding of how heat is distributed among your batteries. So if you see right here, the maximum temperature reached within this localized zone is 66.7, whereas for 2 mm, the heat is kept at 42.4. Right? Now, there are different configurations which we can employ. So rather than having a box type, we can also employ sort of a sharp cone or sharp nose kind of a configuration where air flows through each individual batteries. This depends on how your battery pack should be designed and how can be kept. But it depends on a case-to-case basis. Now, coming to liquids, the Tesla Model S, Model 3, BMW i3, i8, there are many such EVs which are now employing, liquid cooling systems highly, because liquids have higher heat retaining capacity. So various fluids such as your water, DNS water, a mixture of ethylene glycol, water, then mineral oil, and then your nano fluids, the aluminum oxide with water, the amount of particles that you want to employ also depends heavily on how your heat transfer will be. So there are these different fluids that you can use for your liquid cooling. The major added advantage is that, you can very quickly cool down. So for instance, if it is kept to air, open air, and it is not convected properly, in this instance, the average temperature increases from 29 to 69.5 at just 1.5 C. Whereas, with liquid cooling, this can be reduced quite dramatically. If you can see, we have come from 69.5 to 36.6 degrees Celsius. So there is a very well-known advantage to how liquids can really help reduce the amount of temperature that is generated within fluids. This depends heavily also again on the flow rate that you employ versus what liquid you're going to use. But liquids have an added advantage over gases. I'll just quickly cover the PCM also. I apologize. I have very less amount of time with me. After this, I have to show one application problem also. I'll just quickly cover PCM-based cooling also. Now, PCM or phase change materials are one such material which, have the added quality that they can retain heat, or they can absorb enormous amount of heat. This which gets produced by the lithium-ion batteries. Now, this heat is essentially getting transferred from the batteries to a compound. This compound then undergoes a phase change. This phase change then essentially signifies that heat has been transferred, and this helped the material to move from one phase to another phase. Now, various examples are your metal foams, metal fins, expanded graphite, etc., which enhance the thermal conductivity. Idea essentially is that your batteries are covered in such a substance. For instance, this is copper fiber paraffin, CPCM. This can effectively, enhance your heat transfer, and uniformity of battery temperature within a 2 degrees Celsius difference means that for a localized hotspot within this region, this compound, the CPCM, can distribute heat in such a way that there is no more than 2 degrees Celsius difference between one cell to another. So initial and final temperature of CPCM was found 29.6 to 38.7. In that, the heat is getting absorbed, and the final product looks somewhat like this. Again, there is the concept of fins. I can quickly ask a question also. So if you guys have noticed, for two-wheelers in India, which run on petrol, there are always going to be these fin-like structures that are present on the engine. Now, the number of fins and their size itself is it varies from engine to engine, but for many, essentially all the bikes, there is going to be these fins. What do these fins do? These fins are going to carry heat away from the battery, and they're going to open this channel between battery to open atmosphere so that heat is transferred effectively, or the heat transfer is more. So by employing your fins of different configurations on the PCMs, it was observed that longitudinal fins were more effective for this configuration. In that, when you keep the fins in such a configuration, there is more amount of surface area through which heat can be carried and can be expended to this phase change material. Again, this is for this specific case, and this can vary from case to case as well. Now there are different such configuration where you have PCM plus liquid cooling. In that, for the first point, there is a modified silica gel in which all the batteries are kept. This silica gel is going to be the first line of defense through which heat is going to get transferred. Along with that, outside the graphene oxide or the modified silica gel, there will be a water cooling module. Through this water cooling module, water will flow and it will carry the heat that is transferred to the silica gel away from the silica gel to the outlet. So there are these combined sort of techniques that you can employ also based on your use case. Now, the added sort of complexity is that this comes with a lot of operating and maintenance costs, because there are multiple moving parts that you need to be wary of, and you need to have a regular sort of a checkup on how each individual component is behaving. Also, the manufacturing cost is also something that you need to be wary of. I'll just quickly go through this one part. So this is one such analysis that we carried out. Let's say there are very simple batteries kept within a battery pack, 7 batteries, 7 by 3, whole 21 batteries. This is your computational domain. There is an inlet, then there is an outlet. Then these are kept at batteries as a battery walls. This is the mesh that we were able to make. The total number of elements reached somewhere here. The element size was limited to 2 mm, and we kept inflation layers also, so that your information is traveled from batteries to air domain in an effective manner. The solver that we used, pressure based, since the Mach number was less than 0.3. The viscous model that we used was K epsilon, and so on and so forth. Once we are done, this is sort of what we ended up with for temperature. If you can see from inlet to outlet, as we kept moving away, there are these localized zones. So the heat is getting carried from the first cell to the last cell, and this is causing the last cells to have an increased heat, or the heat air is carrying is getting deposited to the last cells also. So this, why you use pressure based solver a bit more. Okay. So within any CFD solver strategies, there are 2 ways in which you can solve your Navier-Stokes equations. There is your pressure-based solving versus density-based solving. Density-based essentially comes with it where cases where we really see significant changes in density of the fluid under consideration. For cases where the Mach number, or the speed at which your fluid, velocity at which your fluid is going to flow, is considerably high. This we measure it as above 0.3 Mach number, because Mach number is a measure of how quickly a fluid is moving against speed of sound. Why speed of sound is relevant here? Because speed of sound is the minimum speed at which pressure fluctuation can travel within that medium. So for any pressure fluctuation to move within air, it will only travel at 330 meters per second at air standard conditions or at sea level. Now, for our intents and purposes, within this battery pack, the velocity is hardly reaching 10 meters per second. So for that matter of fact, the velocity is quite low for us to see any significant density changes. Along with that, because of temperature changes, the temperature is also not quite high so as to, uh, you know, tell us that the air is undergoing a significant density change. We can essentially solve for the density using the equation of state and the pressure-based solver. So for that matter, in this instance, we have only used the pressure-based solver, right? Okay. Uh, Flow over buses, do we use density-based or pressure-based? Uh, it depends on what you want to study. So for case of a flow over a bus will not go above and beyond certain speed. I will not recommend using a density based solver there. Now again, these days for solvers such as your ANSYS Fluent, let's say, there is no real distinction between if you are using pressure based versus density based solver, because certainly you can, but the equations that come with density based solver have to be solved a bit differently than you do with pressure based. And at the same time, for a density based solver, uh, if you want to use a pressure based solver for a changing density case, you can very well employ a model or a function through which your density is changing in your material properties itself, so that you have a measure of how your density is going to vary over a certain distance, certain time, because of certain other variable, and then you can employ that to calculate changes in your density. So it all comes down to what is the computational resources you have available with you, what is the amount of time you can spend on the CFD analysis. That is a major factor. Along with that, for case such as your flow over a bus, which is quite low speed, you can't really expect your density to change as much. So I would recommend pressure based. Okay. Very quickly, I want to show one simulation with me. Very sorry, I have gone a bit overboard. Give me just a moment. Right. Is my screen visible? Okay, it is great. So this was one such case where, a simple solid block is taken. This is using OpenFOAM, a simple solid block with no cooling. Yeah, a simple solid block with no cooling. This is kept at natural convection. We are trying to understand, for a certain amount of heat given to the battery, how will this really fare? Uh, so uh, so if you can see, this essentially is what the distribution of air around my body looks like. Idea is that if my body is kept at, now this is a really, uh, hypothetical case, in that I have given a constant source of heat that is going to be given to this body continuously. Give me just a moment, I'll let you know. Right. So a constant heat of 5v7 watts was given. So over each second, 5v7 watts of energy is given per volume, volume specific heat is given to this battery. So obviously this module will keep on increasing to a temperature which is non-physical. In this case, it's around 7,700 degrees Kelvin, which is really not physical. So in this case, for such a high temperature of air, the high temperature of the battery, the air has quite uh, turbulently moved around my body, and it has reached, if you can see right here, see the temperature maximum reaches at 67683. This is very non-physical, whereas the velocity is kept somewhere around 1.9. Now during the beginning of my simulation, if I can see, the temperature is steadily increasing second on second to 350 to 367, and so on and so forth. and the velocity very close to this battery is going to be higher, because at that point the temperature is quite high. Since temperature is high, the density in air is going to reduce, and due to buoyancy, the air will try to rise up. Now, when air tries to rise up, the velocity in this particular point of time in space, the velocity will increase. So these tubes or these threads signify the velocity streamlines, or how your air is going to behave around the battery, right? Okay. Unfortunately, that's all the time I had for today's session.